Hi and hello. Welcome to our channel named Exploration. My name is Sami and today we will going to start about heap. Now, before going to that, let's analyze something. When we have given an unsorted array and we have to insert the value, right? So since it is unsorted array, we can insert at the last level. Now to insert at the last level, we have to go at n plus 1 index, right? So to go at n plus 1, it will take order of 1 time, and to insert the value, it will take order of 1. Right, so overall it will take order of 1 time. Now to search the value at unsorted array, it will take order of n time due to linear search. Now to find the minimum, this will also take order of n time. Now to delete the minimum, this will take order of n time, because first we have to search the minimum and then we have to delete it. After deleting, we have to shift the remaining elements to the right place. Now what if we have sorted array? Now to insert at the sorted array, in the sorted array, first we have to find the index first of the element, because it is sorted. So to find the index, it will take log n time. Now after that, we have to make that place vacant. Due to this, we have to shift the elements towards right. So to shift the element towards right, it will take n time. Due to this, it will take order of n. Now to search the element in the sorted array, this will take log n because of binary search. Now to find the minimum, how much time it will take? This will take order of 1 time, because let's say the arrays are arranged in ascending order, so the minimum element will be present at the first index, so this will take order of 1 time. Now to delete the minimum, what we have to do, we have to delete the first element and then the remaining element should be shifted towards left, so this will take order of n time. Now what happens if we have a linked list? Now to insert the value, it will take order of 1 time. We can insert anywhere. Now to search the value, let's say this is unsorted linked list, we have to do it linearly, so due to this it will take order of n time. Now to find the minimum, this will also take order of n time. To delete the minimum, it will take order of n time. Why order of n time? Because first we have to search the minimum element, and then using constant space we can do some manipulation, so this will take order of n time. Now let's come at heap. Now heap are of two types. Actually heap are of many types, but we will study only two heap, that is min heap and max heap. What is min heap and what is max heap, we will study it later, but understand that at min heap the root node will always be minimum, right? So to insert the value at min heap, this will take order of log n time. Now how it will take, we will understand it later, but observe here, for time being let's do not consider this part. Now to find the minimum element at the heap, it will take order of 1 time. Why? Because since it is a min heap, the minimum element will be always at the root. Now to delete the min, this will take order of log n time. Now we can see that this one is efficient, this one is also efficient, and this one is also efficient. So due to this, in many problems we use heap data structure, right? So due to this, we will study heap now. Now to study heap, we have to first understand some basics of tree. So first let's understand the basics of tree, and then we will start with heap. Now there are many types of tree: binary tree, ternary tree, canary tree, but we need only binary tree here. Now the property of binary tree is that every node will have either 2 children or 1 child or 0 child. Okay, now what is node? Node is nothing but you can say a vertex. So we represent node in this form, and now with node there is one link attached, also called as edge. Now we have a tree with one node will look like this. Now with a tree with 2 nodes, there will be a root, and a root will have a left child, or a root will have a right child, right? Now what we have a 3 node, in this case a root will have its left child and this node will have its left child. Similarly, observe here, a root will have a right child and this node will have a right child. This is nothing but called as a skew tree, that is, it is tending towards left only or right only. Now observe here, this root will have a left child and this node will have a right child. Similarly, this root will have its right child and this node will have left child. This is actually in which a root will have both the child, left child as well as right child. Now there is one more term in binary tree that is known as almost complete binary tree. Okay, let me first write the definition. So here all the levels are completely filled except the last level. What do you mean by levels? These are the levels. So this is nothing but a 3-level tree because it has 3 levels. Now here all the levels are completely filled except the last level. There may be a missing nodes at the last, but the nodes will be filled from left to right always. Okay, so there will be no vacant space between the nodes at the last level. Observe here, at this level the nodes are completely filled, at this level the nodes are completely filled. This is the last level, but we can see that here this node is missing, but since all the nodes are filled from left to right, there is no vacant space between the nodes, so we can say that this is a ACB tree, that is almost complete binary tree. Now what about this tree? At this level it is completely filled because it is a root. At this level you can see that the root is missing its right side, right? But we can see that this is not a last level, this is the second last level, and here this node is missing, so this is not a almost complete binary tree. What about this one? We can see that this place is missing, this is also not a complete binary tree, and this is also not a complete binary tree because this node is missing. Okay, I hope you got it, what is almost complete binary tree. Now there is another term that is known as complete binary tree. Let me first write the definition. So here all the levels will be completely filled, including the last level as well. So this level is completely filled, this level is completely filled, and this level will also be completely filled. There will be no stall or vacant space between the nodes. Similarly, this is completely filled and this is also completely filled. What about this one? Now we can say that there is only one root present, and since we will consider that this is the last level and it is completely filled, so this is also a complete binary. Okay, now as I said earlier that this is a level, this is level, this is level, this is also a level, and this is the last level. So how we call which level are these? So this is nothing but a 0th level. This will be the first level, this is second level, and this is third level. So we call this as a 4-level CBT, complete binary tree. Now let's go further. I hope you got what level is. Now observe here, at the 0th level how many nodes are present? We have only one node, right? At the first level how many nodes are present? We have 2 nodes. At second level how many nodes are present? There will be 4 nodes, right? So 4. Why 4? Because there are 2 nodes, and since it is a complete binary tree, this node will contribute 2 extra node, and this node will also contribute 2 extra node, right? So 4 node. Now what about the third level? There will be 8. Now 1 can be written as 2 raised to 0, 2 can be written as 2 raised to 1, 4 can be written as 2 raised to 2, and 8 can be written as 2 raised to 3. Now there is a question that if we have a k-level CBT, then what will be the number of nodes? Now at the 0th level there will be 2 raised to 0 node. At the first level there will be 2 raised to 1 node. At second level there will be 2 raised to 2 node. At third level there will be 2 raised to 3 node, and so on. It will go to 2 raised to k minus 1. Why k minus 1? Because when we have a 4-level CBT, then the last level is actually called as a third level, right? So when we have a k-level CBT, the last level is actually k minus 1. Now we have to solve this. This is the GP formula. Here a is 1, common ratio, that is r, is 2 raised to k minus 1 upon 2 minus 1. So this will be 2 raised to k minus 1. So when we have a k-level CBT, number of nodes will be 2 raised to k minus 1. Now only this much basic we want to understand heap. So in the next lecture we'll be starting heap. Okay, so thank you.